Hello and welcome back to another video, guys. In this video I will show you how you can use voice cloning for any language, and for this we will use the Tortoise-TTS model and fine-tune it for any language. In my particular case I will fine-tune it for the German language, but I will also show you how you can fine-tune the Tortoise-TTS model for your language. And as always, I would say we just jump right into it. Let's go. But before we start, I have great news for you guys. One of you can win this NVIDIA RTX 3080 Ti GPU with 12 gigabytes of VRAM, Tensor cores, and 912 gigabytes a second memory bandwidth. And what do you need to do to win this GPU? First, attend to NVIDIA's 2024 GTC conference, and second, send me a screenshot as a proof of attendance. That's it. The GTC conference is happening online and in person. In case you haven't heard about the GTC conference yet, the GTC conference covers a wide range of topics in the field of AI, giving you a great idea of what's coming next in AI. There are more than 600 sessions, and people from all major players in the field of AI like Meta, OpenAI, Google DeepMind, NVIDIA, or Runway ML will be holding talks and sessions. And personally, I found the What's Next in Generative AI, the fastest stable diffusion in the world, as well as the human-like AI voices, exploring the evolution of voice technology, talks very interesting. And yeah, good luck to everyone, and don't miss out on this one. Alright, and the first thing that we need in order to be able to fine-tune the Tortoise-TTS model is a dataset that contains speech data of a particular language. So for example, I will fine-tune the Tortoise-TTS model using a German dataset. And in particular, I will be using the following dataset, which stems from a paper published in 2021, and it contains a high-quality text-to-speech dataset that contains 97 hours of audio from 117 speakers. And you might be thinking right now, okay, well, he's using an already existing dataset, but where should I get my speech data or audio data from in order to be able to fine-tune the Tortoise-TTS model? And I have to say, that's a very valid point. And if there wouldn't be already an existing German dataset, I would ask the same question. So for that reason, in a future video, I will show you how you can create your own audio dataset from publicly available speech data. And if that sounds interesting to you, make sure to subscribe to my channel. But for the rest of this video, I will show you how you can fine-tune the Tortoise-TTS model for any language if you already have an existing speech dataset in your particular language. And the first thing I needed to do is to download the dataset that I mentioned, and it contains around 15 gigabytes of speech data. So this can definitely take a while. You can see here that the estimated time to download this is around 12 hours. So I will fast forward this step. And yeah, don't worry, this is not usually the case, but I think the server is pretty slow, so I can't download it faster. Alright, and once you have your dataset downloaded, we need to format the dataset to the LG Speech format. And LG Speech is also a publicly available dataset. That's where the name convention is coming from. Imagine you have one folder called dataset, and in this folder you have all the audio speech samples with the following naming convention. So you see the sample name, which can be a number or a more descriptive text of the audio speech, but basically just an identifier. Then we have the ending point waveform file, and then we have a pipe as a delimiter, and here we have the transcription of this file. So the transcription of the speech file that we have here is contained in the file name. This is the LG Speech format, and then we have basically one big folder containing all the speech samples, and in their file names we have the transcriptions. And this is basically the first pre-processing step, formatting your speech dataset to this format so we can use the dataset to fine-tune the Tortoise model. And I have already done this before recording this video, so I skipped the 10 hours of downloading this dataset, but here's the code to format this dataset to the LG Speech format. For this, we first need to unzip the dataset. Then we adjust the dataset structure so that all train and validation waveform files are located in an individual folder. So this dataset has a nested structure, and we want to overcome this by putting all the waveform files in one folder called dataset, and therefore we iterate through the nested files and also add the transcription, which is always saved in a metadata CSV file. And then once we have an array containing tuples of the old path and the new path that we would like to create, we then divide this dataset into train and validation subsets, and here we use a ratio of 85%, so 85% of all the speech samples will be used for training and 15% for validation. Then we create a folder called dataset, and in this folder also a subfolder called waves, and then in the waves folder we will store all the speech samples, and in the dataset folder we will store 2 text files called train and val, or validation, containing all the file names of the training data and the validation data. And then basically as a last step we can create a zip file for this dataset folder, and I have done this previously, that's why I didn't download the whole dataset again, but this is basically the code I use to transform this dataset into a LG speech format, which I then can use in the next step. And in case you're thinking, hey, I actually would like to create my own speech dataset, but how long should one audio sample be and how should I construct the dataset? As I mentioned, I will cover this in a future video, but for now I would recommend you to either search on Google for TTS dataset and then your language, or check out Hugging Face, where you can click on datasets and then activate the text-to-speech filter, and here you can see that there are 122 publicly available speech datasets. For example, here you can see Ukrainian language, English dialect, Chinese or Swedish. So those are some recommendations from my side, which can also save you some time. Here you can also see for the dataset that I used, the samples have a minimum of 5-second length, and the majority of them are shorter than 15 seconds, as you can see here. And the overall average is 9.5 seconds for the speech samples I used. Now that we have our preprocessed dataset, we can move forward and adjust the code that we will use to fine-tune the Tortoise-TTS model. And for this we will add special letters for our particular language. So for example, for the German language, I will add the following letters, which are Ä, Ö, Ü, and S, or like it's pronounced a double S. And per default, the Tortoise model is trained for English language and therefore also only supports letters of the English alphabet. And since you probably want to support all the letters that are used in your alphabet, we need to manually add those letters to the vocabulary. And for this we need to make some adjustments to the fine-tuning code that is available at this GitHub repository. And all the changes that are necessary I've listed here. And the first thing that we will do is open this repository, and I would recommend you to fork it. So you click here on fork your own copy and just create the fork. Alright, and now you can see I forked this, and then you can click on this link, and I then typed git clone and copied the link of the repository to download or clone the repository to my local computer, and opened the repository with my local IDE, which in my case is Visual Code, but feel free to use your preferred IDE, doesn't matter at all. And here you can see I now opened the forked repository on my local computer, and now we can go back to the list of changes that we need to make, and we will start with the cleaners.py file, which is stored under the following path. And in this file you can find at the very end the method called English cleaners, which takes an input text and more or less normalizes or transliterates input text. So you might be wondering what's exactly going on here. So we can see we converted to ASCII, and I looked into it. The Tortoise model uses the UniDecode module, and here we can see for this input text the output is the following. So we kind of normalize it and convert non-ASCII characters to ASCII characters. So it is safely encoded to ASCII in a way using this module. And since those characters or letters are exactly those we are interested, if we are working with languages that are not English, we obviously want to keep those letters. And for this reason, we need to alter or adjust the code here. And I used the following replacement, which we can see here. So I used the library German transliterate, which already does a lot of the heavy lifting for me, and you can find the repository here. And what this does is to give you a brief idea of how this works. So for example, using the we can transliterate abbreviations like ABC into a phonemic version, and this is the German pronunciation, which will be ABC. Therefore, if this is our input text, this will be the result of our transliteration. So it's less about the actual letter and more how it sounds to us. And here we pass our input text to this library, which does some of the work, but otherwise just imagine that here you want to make sure that the text that you pass to your model is clean. This kind of adds a safety level to generating good quality speech results. And then we transform the text to lowercase and remove multiple white spaces, and then we also remove any quotation marks in the text. And since I also use this library, I need to import it at the beginning or the start of the file here, and that's it. Then we can save this file again. And in case there is no transliteration library for your language, what you can see here is kind of what such a library does. So you have abbreviations like Mrs. or Mr. And here is the way it would be pronounced, and this is the abbreviation. You kind of have like a dictionary in which you replace all those inputs with the phonemic version of the abbreviation. So you could craft yourself such a normalization step. But as I said, it makes the generation of speech overall more robust, but it's not a mandatory step to 100% replace this for your language. Then we can move on to the next file, which is this one, and add special characters to the letters variable, line 12. And this file is in the same folder here called symbols. And what we will do here is just at the end add our special characters. So for me, those would be the following. And here we also add them in uppercase. I'm not sure exactly why those are also added in uppercase, because internally we don't process those uppercase letters, but just to be safe I also added them here in uppercase. And then we go to the experiments folder and copy the example GPT YAML file, and this one we rename to custom language GPT.yaml file. So here we have our custom language file here, and then in line 1 we can type custom language GPT. Here we can replace this with just train dataset. Then we change the path of our training dataset to this one and add in line 29 as a new line a new attribute, the tokenizer vocabulary, because we use a custom tokenizer in our case for our specific language. And then we do the same for the validation dataset, where we name it val dataset, change the path to this one, and then as well add at the end the tokenizer vocabulary. And then as a last step, we will change the number of iterations from 50,000 to 5,000 just to make the fine-tuning shorter. And yeah, that's all we need to do for this file. And then we can also save the custom language GPT YAML file. Then we will open the .getignore file and add the following statement. Important is the exclamation mark, which excludes our custom language GPT YAML file from the ignore list. So up here it stated that all YAML files should be ignored, but with specifically stating this at the end of the file, this rule will be overwritten and our custom language GPT YAML file will still be added to our GitHub repository. Then we will open the requirements lags text file, and this file is stored inside the folder codes. And what we will do here is add a specific module version of the transformers library, because using a newer version led to an error for me, and therefore I fixed the project version to 4.29.2, which makes sure that the fine-tuning code will work. And while fine-tuning, I ran into an error which was caused by the util.py file, which is stored under codes, utils, and then util.py. And here we need to replace this statement in line 25 by the following. So it seems like this is deprecated, and the new way to import the infinity is right away from Torch. So also make sure to make this adjustment to the code to be able to run this code. And then we also save this one. And then we will add all our changes to the repository by first typing in git add period, and then just git commit -am and calling it changes for custom language fine-tuning. Alright, and then I'll just push these changes to my Git repository. Technically you could just work on your local computer in case you have a local GPU. Otherwise, I would recommend to create a fork and also push your changes to your GitHub repository, and then you can, for example, use a Cloud GPU or Colab to use the changes made. Alright, and what we then can do is either return to our notebook or just run this notebook inside your forked repository. In case you're still working, for example, on a Cloud GPU instance like a Colab notebook, you can then clone your repository using the git clone command. As you can see here, I'm cloning my forked DL Art School repository. And then I navigate into the DL Art School directory or folder and then to the codes folder. And in there, I will install all the required modules using the requirements.lags.txt file. And we can just run the cell by typing command enter. Alright, once all required modules are installed, we can then move on and download the model weights for the vector quantized variational autoencoder and the autoregressive model, which is a GPT-2 model. And in this video we will fine-tune the autoregressive model. The Tortoise model or Tortoise architecture overall consists of 4 models, which I've recently covered in a series of videos. Feel free to check them out to further understand the meaning of the vector quantized variational autoencoder and the autoregressive model. And to download the model weights for both models, we will run the following cell. And once the model weights for both models are downloaded, what we then will do is create a text file that contains all transcriptions as a source to train a tokenizer. And with all transcriptions, we mean all the transcriptions inside our data set, including the training and validation subsets. And since this is also the data that we expect during our training and also later during inference, the transcriptions are perfectly suitable to train a tokenizer. And you might be wondering, especially if you have some experience with large language models, why would we now train a tokenizer? Because usually if you train a tokenizer and then train a large language model on tokens that are encoded by a tokenizer, you can't replace or exchange the tokenizer after the training. So there is a strict dependency of the large language model toward the tokenizer. And in this case, we have a GPT-2 model which generates MEL tokens. And you might be wondering, why would we now create a new tokenizer? Because the model also learned to understand the tokens encoded by the tokenizer. And I find this very confusing, but for some reason it actually works if you train a new tokenizer and pass it to the model. So the model is during fine-tuning able to adapt to the new tokens. I'm kind of curious how much the model actually relies on the tokens. So feel free to, additionally to this video, do some more experiments on why the tokenizer actually can be replaced, and you can still obtain great results with fine-tuning the autoregressive model of the Tortoise architecture or Tortoise model. And to create the text file containing all transcriptions, we iterate through the training and validation subset. So we read the train text file and also the validation text file, in which all the waveform files are stated. So we iteratively read the lines, and then for each line, which is one waveform file, we split it by the pipe. By using the second element, we obtain the transcription, which we then can strip. And then by prepending a blank, we can create a, let's say, fluent text. So all the transcriptions are just separated by a blank, which is kind of just a big, very big text. And this serves as an input to our tokenizer. And then we write this text containing all transcriptions to the transcriptions text file and can then use it as a source to train a tokenizer. And if you want, after running this, you can also have a quick look at the transcription text file by just running the command cat transcriptions text file. And here you can see the content of the file. And if you're not from Germany or don't speak German, this probably doesn't make much sense to you and it's hard to read, but I can confirm this is German. So this we will use to train our tokenizer. And to train the tokenizer, I first wanted to use the voice tokenizer.py file inside the fine-tuning repository, but for some reason there were some issues with relative imports, and I think the code was written for Python 2. So since it's sent to me to be a little extra work, I just decided to copy the code to train the tokenizer because it's not all that much. All you need to do inside this code is to first exchange this text cleaners method. And here we use the same code that we have used earlier to alter the method English cleaners inside the cleaners.py file. So you can just copy the method English cleaners from this file and paste it here. And again, I'm using the German transliterate library, but as I said earlier, you not necessarily need to use such a transliterate library. It just overall improves the speech quality when, for example, having abbreviations. And then there's another method to remove punctuation. So in a way, again, cleaning the input text. And one more thing that you need to do is to add the special letters for your language. So there is a regex that allows only a certain set of characters to be in the input text. And by default, it's from A to Z, only lowercase. So what I did, I added those 4 letters. So the Ä, Ö, Ü, and double S in German language. And yeah, for your language, just remove them, and whatever is needed, for example, an E like that. For Spanish, just add the letters that you need for your language here. All right, and then you can just run this cell by pressing Command Enter as always. And this might take like 20 seconds, depending on how much transcriptions or text data you have. And then the tokenizer will be saved as a JSON file. And basically the tokenizer learns to efficiently represent your language in specific tokens. Depending on the language, sequences of characters occur more often or less often. So this is individual for every language, and therefore kind of makes sense to train a tokenizer that is optimized for your particular language. And here we can see this is done. And then as a last pre-processing step that I haven't mentioned in the start, but it's definitely important for the Tortoise model. The Tortoise architecture or the Tortoise model takes as input audio samples with a sampling rate of 22.05 kilohertz, and the dataset I was using had originally a sampling rate of 44 kilohertz, so I had to resample all audio samples. In case that's also the case for your dataset, I just pasted the code that I used here, but in case your dataset already has a sampling rate of 22.05 kilohertz, you can just skip this step. And what this code basically does is it checks for each of your audio samples if it has a sampling rate of 22.05 kilohertz, and if it doesn't, then the audio sample will be resampled, and then the waveform waveform audio will be overwritten with the new sampling rate. And yeah, feel free to use it in case your dataset doesn't have already a sampling rate of 22.05 kilohertz. Alright, and now after all the prep work, we're finally able to fine-tune the autoregressive model of the Tortoise architecture. And for this, we just run the following statement while using the training.py file and passing our custom language GPT YAML file or the config file for our fine-tuning that we have created and edited earlier. And yeah, as always, just type Command Enter and then we can run the fine-tuning. And this can, depending on the GPU that you're using, take hours to even a day. So maybe grab 1 or 2 cups of coffee and watch a movie and then come back and explore the fine-tuned Tortoise model in your language. And when you run this, you should see something like the following. So first we can see all the training arguments that we have defined in our configuration file. Then we can see the model architecture and also that the model was loaded here, and then start of the training. So here we see the first epoch, which has the number 0, and during one epoch our model is trained on the entire training data set. And we can see for our training data, one epoch contains 160 steps, and in total we train our model for 5,000 steps. So the model will roughly be trained for 30 epochs. And if you feel like the training takes too long and you're eager to check out how the fine-tuned model works already, you can also at any time just stop the model by pressing, for example, this button. And what I would recommend you, in the config that we have chosen, every 500 steps a model checkpoint will be saved. So you can always see here the step. So this is step 1000, and at step 1000 one model gets saved. So you can see here info saving model. Then at a later step you can see again 1500 model gets again saved. I'm honestly not 100% sure when the model will change, and I think this is also dependent on the size of the dataset. So feel free to interrupt the training of the model, but what I would recommend you to do is to make sure that you interrupt the model basically at for example, step 2000 or 2500, because if you would interrupt the model at step 2300, you would lose the training progress of the last 300 steps, which you obviously don't want. And in case you figure out that the fine-tuned model isn't as good as you would like to, you can always resume the training. And for this you can change in the custom language GPT YAML file in line 122 the pre-trained model GPT. And here, instead of using the autoregressive model or model path, you will here pass your training checkpoint file, and therefore can initialize the autoregressive model with your training checkpoint and continue training your already fine-tuned model. And then once you're done with the fine-tuning, you can find the checkpoint of the fine-tuned model under this path. So it's in experiments, custom language GPT, and then models. For example, we can have a quick look and see here there are 5 different checkpoint files of the model weights for the fine-tuned GPT model. Here we can see it after 500 steps, 1000 steps, and the most progress with 2500 steps. And this one we will also use. Now you might ask yourself, okay, now we have this fine-tuned GPT model, but how can we now use it to generate speech? And that's an excellent question. And this question we will cover in part 2, in which I will show you how you can ingest the inference code of the Tortoise model so that it can also generate speech for your language. And in that part 2 video, I will also share the winner of the RTX 3080 Ti NVIDIA GPU. So definitely make sure to also watch the second video. And as always, I would appreciate if you subscribe to my channel and like this video. And I'm looking forward to seeing you in the next video. Bye bye.